face retouching has come a long way and shows up everywhere, from live filters to film post-production. Still, many methods face a core dilemma: they either keep the image globally consistent or they preserve tiny local details, but rarely both. We tackled this problem from two angles. First, we built a large-scale benchmark to fix the data shortage. Second, we designed a new framework that combines frequency selection and restoration, or FSR, with multi-resolution fusion, MRF. Together, these let us remove blemishes while keeping natural skin texture and global harmony. Our approach is inspired in part by ideas from JPEG quantization, but learned end-to-end so the model decides what to keep and what to suppress. To train robust models, we need realistic, varied training pairs. We generate our dataset using a controlled three-stage pipeline. Step 1 uses 3 pre-trained diffusion models to produce 23,760 base portraits from 7,920 combinatorial prompts that cover 7 attributes like age, gender, hairstyle, and facial shape. Step 2 applies a FaceNet-based segmentation to split the face into 11 regions, which lets us localize where blemishes should appear. Step 3 uses low-RA-tuned models to inject blemishes, moles, freckles, and acne into specific regions at controlled intensities, mild, moderate, or severe. This gives us aligned before and after pairs with realistic, diverse blemish patterns for training. The final benchmark contains 25,000 high-quality image pairs, that is, before and after retouching pairs, and includes a curated subset of 1,240 especially high-quality faces. We designed descriptive prompts by combining categorical attributes, age groups, gender, beauty condition descriptors, hairstyles, skin tones, ethnicities, and detailed facial subfeatures like lip shape, nose type, eye size and eyebrows, plus expressions. The generation ran on NVIDIA RTX 4090 GPUs for about 206 hours, averaging 45 to 60 seconds per image pair. We split the data October 10, 80 into training, validation, and testing sets, ensuring broad coverage across facial variations so models trained on the dataset generalize better. Our dataset includes numerous paired examples where each clean portrait is matched with a blemished counterpart. These pairs come from multiple diffusion backbones, so you see stylistic diversity across samples while maintaining alignment. The variety ranges from subtle freckles to heavier acne and distinct moles in different facial regions. Because the pairs are aligned and annotated by region and intensity, the network receives clear supervision about what to remove and what to preserve, which is essential for learning precise, localized repairs without harming surrounding texture. Our repair pipeline is straightforward and effective. First, we decompose the input into a Laplacian pyramid to capture multi-scale representations and to isolate high-frequency components that encode texture. Second, a soft mask generation branch, or SMGB, predicts soft defect masks so the repair is focused where it's needed. Third, the frequency selection and restoration, or FSR, module filters and restores frequency components while projecting corrections back into the spatial domain. Finally, multi-resolution fusion, MRF, upsamples and refines the multi-scale outputs, blending in high-frequency details to produce a final high-quality, blemish-free portrait. In short, multi-scale decomposition, targeted masking, frequency-aware restoration, and progressive fusion. FSR is the heart of our framework and consists of 3 components: frequency-aware dynamic aggregation, space-domain projection, SDP, and a selective frequency feed-forward network, SFFN. The first idea is to treat blemishes as mostly frequency-specific disturbances. We learn to reweight and suppress those unwanted frequency bands while preserving bands that encode pores, hair, and other fine details. Inspired by JPEG, we introduce learnable quantization matrices that adaptively downweight frequencies carrying blemish signals. After frequency domain processing, we refine features in the spatial domain via SDP. Concretely, we normalize features and project them into query, key, and value tensors similar to attention, but these projections operate on features that have already been cleaned in the frequency domain. This makes the spatial attention focus on real structural details rather than blemish noise, sharpening textures and correcting artifacts that filtering might introduce. SFFN further boosts representational power by selectively retaining critical frequency components. Think of it as an adaptive, learn JPEG-like step. Instead of fixed quantization, the network learns which frequencies matter for perceptual quality and which can be suppressed. This selective feed-forward stage helps the system keep pores, hair strands, and other fine structures while removing blemishes robustly. MRF simply combines the strengths of low and high-resolution features. We upsampled the coarser result, attached the missing high-frequency details from the Laplacian level, run a couple of small convolutional refinements, and add back a residual. Repeating this from coarse to fine removes large blemishes while restoring skin texture, yielding a clean, detailed portrait. Overall, by combining large-scale, carefully synthesized training data with a frequency-aware, spatially aware restoration pipeline and multi-resolution fusion, we achieve consistent, high-fidelity blemish removal that preserves natural texture.